Hey everyone, welcome to my channel. I have started a personal DSA challenge where I am solving 5 problems per pattern, covering 180 problems in total. I'll be posting one video per day explaining my thought process from brute force to optimized approach. If you're new here, you can check out the previous videos to follow along. In today's video, we will work on Fibonacci series. So the problem states that we are given a number n and we need to return the nth Fibonacci number. So for the brute force approach, we can use recursion, and for the optimized approach, we can use dynamic programming approach. In this next coming 5 questions, the flow would be brute force would be recursion and optimized solution would be of dynamic programming approach, like how we write the recursion code and how we convert that recursion code into dynamic programming approach. So Fibonacci series is nothing but the initial numbers f of 0 is 0 and f of 1 is 1. To find f of n, it is nothing but f of n minus 1 plus n minus 2. So if you consider 0 as 0 and 1 as 1, the third number would be 0 plus 1 1, then 1 plus 1 2. It is nothing but the sum of last two elements. 1 plus 2 3, 3 plus 2 5, 5 plus 3 8, 8 plus 5 13, and so on. So whenever the question here, if you see, the question states that they are asking for n equals to 2 value. So the second Fibonacci number would be 0 plus 1, which is the second number is 1. And here if you see the third number, so this is not considered. This is the this is not considered. This is the first number, this is the second number, this is the third number. So n equals to 3 gives 2, n equals to 4 gives 3, and so on. So the recursion approach for this would be we are simply translating this code into this formula into the code. That is it. Here they said that this formula applies only when n is greater than 1, but for n equals to 0 the answer is 0, and for n equals to 1 the answer is 1. So we will first write it. If n is they have already told that n starts from 0 and n still ends at 30. So we can say if n is less than 1, less than or equals to 1, I would say, then we would return n. So if n is 0, 0 is less than 1, true, so it will return 0. And so f of 0 would be 0. If n is 1, this would be true and it will return n, which is 1. So f of 1 would be 1. So this satisfies. Now we just need to return this formula. Fibonacci of, in place of n, we need to pass n minus 1 plus n minus 2 plus Fibonacci of n minus 2. That is it. Let's run the code. It is accepted. So even though this solution is very clean and intuitive, it has a major problem. That is, the same values are calculated again and again, which leads to huge recursion tree. For example, if n value is 5, then we would call 4 and 3, right? And for 4 you would call 3 and 2, and for 3 you would call 2 and 1, and for 3 you would call 2 and 1, and for 2 you would call 1 and 0. For this 2 you would call 1 and 0, and for this one you would call 0 and -1, but -1 is not in our limits, so we will ignore that. And okay, so it's better to write if n equals to 0, then we will return 0. I will say if n equals to 1, then we will return 1, just to avoid any confusion or any unknown exceptions. So yeah, so here you are calling 3, and again you called 3, you call 2, you call 2, and you call 2. So every time you'll be calculating Fibonacci of 4, Fibonacci of 3, and again you'll be calculating Fibonacci of 3, Fibonacci of 2, which means you are just recalculating again and again. So this will lead to huge recursion tree. So the time complexity would be 2 power n, because we are in each step we are getting two possibilities. For 5 we got 4 and 3, for 4 we got 3 and 2, for 3 we got 2 and 1, for 3 2 and 1, 2 1 and 0, 2 1 and 0, 1 0 and -1. So we are getting two possibilities in each step. So this tree, it is nothing like a binary tree, and the time complexity would be 2 power n, and the space complexity would be O of n, because we are using recursion. So internally it will use a recursion stack, and that's why we use extra space. So now we need to think of how we need to optimize this. So if you use memoization technique, we just need, let me comment this. For memoization technique, we just need a extra dp of size n+1, and we would return, maybe we'll implement a helper class passing the n value and the dp. Now inside that helper class we will return the nth Fibonacci number, so the return type would be integer, and now we are implementing helper. We are passing n and the dp, which is an array dp. Now we are simply copying this and this. Okay, now before returning this, we will check if this is already updated in our dp array. So if dp of that n is not equals to 0, then we will return dp of n. If it is calculated, then we will straight away return that value. If it is not, then we will calculate it. dp of n is nothing but helper of, what are we passing, n-1 comma dp, the same formula, n-1 plus n-2. So helper of n-1 plus helper of n-2. Okay, and then we will return dp. We are updating it and then we are returning it. Let's run the code. Okay, let's submit it. Alright, it is working. So yeah, for the dry run, if you take a dp of 5, we are calling 4 and 3. 4 and 3. since these are not updated, initially the DP would be empty. Okay, initially the DP would be empty. So we will calculate DP of 3 and 2. We will calculate that and we will update it here, and then we'll calculate this and we'll update here. Yeah, if you do the dry run, it would be easy to understand. Otherwise I'll calculate it. For 4 you're calling 3 and 2. For 3 you're calling 2 and 1. For 3 you again call 2 and 1, and for 2 you call, I'll separate it with a semicolon. For 2 you will call 1 and 0. So this 0 would return 0 and this 1 would return 1. Okay, so for 2 it is nothing but 1 plus 0, which is 1. So 2 will be updated with 1, and for 3 2 is already updated with 1. So 1 plus 1, it will become 2. And if n is 1, we are straight away returning 1, so this would be 1. And yeah, that is how we would be calculating for the other numbers as well, and we would be updating, returning whatever number they are intended to call. So now we have learned how recursion works and why optimization matters. So that is it for today's problem, and I will see you in the next one.